Okay. So we are recording to the cloud, and now let me introduce our first work package, which is called New Morphisms of Graphs. However, before I go into math, let me, since I'm the first speaker, let me, oops, one doesn't it? I cannot switch the, I don't understand why I cannot switch the slides. Okay, no matter how many times you test it with Zoom, there's always something wrong going on. Okay, so this is our network as seen from the orbit. So you go to the orbit horizon Europe, and then you see our project. Now it's called Static Change. The previous name, Research Innovation Static Change, was much nicer because we have a beautiful acronym RISE. Well, but this is how it's called right now. And at the moment of application, there were 78 of us, okay, in 26 institutions in North America and in Europe, plus Israel, okay? So here are all the nodes. We also have Hawaii, so Pacific is included as well. And the project lasts full 4 years. It started 1st of January and is to end on 31st of December 2026. And this year is kind of special because for this particular year, 2023, we have, yeah, let me see if it works. Yes, okay, I'll mark it. We have additional funding from the University of Warsaw, from the Simons Foundation. So I hope to see many of you from the US here in Poland. Okay, now we go into math. Since our task is to discuss and discover new morphisms of graphs, let me recall what are all morphisms of graphs. So here is the most obvious definition you can possibly think of. If you have your directed graph, basically a morphism between two graphs is a pair of maps. You have a map from the set of vertices to the set of vertices, and you have a map from the set of edges to the set of edges. And they have to satisfy these two commutation equations. So in other words, the endpoints and the starting points of the edges must be preserved when you do the mapping. Okay. So if you map an edge with F1 and then you take its beginning, it must be the same as taking the beginning of your edge and then mapping it at F0. And then it's the same with the target maps. Okay. Now we will need it very much an assumption that this morphism of graphs is proper. And proper means that both of these maps are finite to one. Okay, this is discrete topology, if you want. So anything compact is just finite. Okay. All right. But we need to fancy into something more refined, and namely something which I refer to as path homomorphisms of graphs. And now the upgrade that we do, now we don't just look at maps between vertices and edges, we look at maps between all finite paths. So FPE is the set of all finite paths in E, FPF is the set of all finite paths in F. And we have a map from one set to another, which has the following properties. First property is that you have to map edges, vertices into vertices. So vertices go into vertices. Another thing is that you have to respect the endpoints and the starting points of paths. So if you take a path and map it to a path in another graph, okay, and then you take the beginning of this image, then it must be the same as taking the beginning first and then mapping it to the other graph next. Okay. Next, if you can, it has two paths that are composable. All right. So if P and Q can be concatenated to a path PQ. Well, then what we assign to a path PQ must be the same as concatenation of paths FP and FQ. And by the early condition, it's obvious that if P and Q can be concatenated, if the end of P is equal to the beginning of Q, then also the end of FP must be the beginning of FQ, right? This goes by the first condition. And likewise, we will need at a certain point, not today actually, but we'll need at a certain point to assume that these maps are proper. And then obviously, again, we can say that that this morphism is proper if f is finite to 1. Another way to think about this path homomorphism of graphs is if you look at a graph that has a small category, you look at edges, at vertices as objects, and you look at paths as morphisms. Okay, so then such a homomorphism of graphs is simply like a functor from one small category to another. Okay, you can recognize it in these conditions if you want to easily remember what path homomorphism is. Okay, so these are our ambient categories. Okay, what we will, I think it was Michelangelo, right, who said that sculpting is just removing unnecessary pieces of marble. Okay, so we are sculpting these pieces of marble. We are removing unnecessary morphisms which are too general, which will not induce star homomorphisms between graph sister algebras. Okay, but these are the ambient categories in which we will carve. Okay, so first, well, that actually has just been defined. Maybe I will explain the title. What do I mean by contravariant and covariant conditions? Okay, as all of you know, because we have a project with graph algebras, whenever I have a directed graph, I can assign to it a Leavitt path algebra or its C-star completion, which is a graph C-star algebra. And when you make this assignment, okay, then you can either take a morphism between graphs and have star homomorphism between the induced graph sister algebras going in the opposite direction or going in the same direction. You have somehow, you know, like you have a group and you go from a group, finite group to a Hopf algebra. You can either go covariantly and go from a group to a group ring, or you can go contravariantly and go from a group to finite functions on a group. Okay, so one construction will be of a Hopf algebra will be covariant, one will be contravariant with respect to homomorphisms of groups. But here what happens is that in both cases have one and the same construction. It's always Leavitt path algebra or a graph sister algebra. Okay. However, we can choose whether our morphisms between graphs are turned into something covariant or contravariant. So when we look at this first ambient categories of the category of graphs and proper graph homomorphisms, that's for the contravariant construction. Okay, so then we'll basically take a pullback of such a proper graph homomorphism to define a star homomorphism between graph sister algebras. Okay, and then when we go to the other ambient category of path homomorphisms of graphs, this will be for the covariant construction. Okay, all right. So that's our first restriction. Basically, you need this assumption in order to induce a functor on path algebras. So that's sort of the highest level of generality. But then you can say, all right, I have something like con path algebras, or if you are more sister-minded, they're called Teplitz sister algebras, which means that you apply on the first type of Kunstkrieger relations. These Kunstkrieger relations which tell you about the endpoints of your edges, okay? That these edges are actually partial isometries with appropriate ranges, okay? And we have a condition which is kind of unexpected. I decided to call it target bijectivity condition, because what happens here is the following. Let me draw a picture. Okay, so to make it more clear, imagine that I have an edge, so I have my graphs E and F. Okay, and here's my graph homomorphism. So in particular, what I can do, I can take an edge X in F1. That's an edge. Okay, and I can take a preimage. As in here, I can take a preimage of X. So this will be something in the E1. Okay, sorry, yes. So it will be, so E is now in E1. Okay, and I'm simply taking all edges that are mapped under F to this particular edge X. Okay, but I can then do the same with vertices. What I do, I take this edge E, which is in the set. I assign to it its endpoint, and of course it is in the preimage by the conditions of what can be considered as a graph, as morphism of graphs. It obviously lives in this set, is in the preimage of the endpoint of X, okay? But what we demand is that the Thus construct map, which is always well defined, but it is actually bijective, okay? So it's best to understand it on an example to remember it. So if I look at the following situation, I have here in E, I have two edges like this, and then I map them into one edge like that. So this is in E, and this is in F, okay? Then this condition is satisfied because this is my X, and this is the end of X. And when I look at the preimage of X, it has two edges, E1 and E2, all right? But when I look at the preimage of this vertex, it also has two vertices here. So that's a bijection, okay? But if you would look at another situation that you have two edges like this, then you cannot map them to one edge like that. All right? Because here what you have, you map a two-element set into a one-element set. Okay? And that's hardly ever a bijection. So that's exactly custom made in order to ensure that the first type Kunst-Krüger relations are satisfied. Okay. Which, if you remember, that's just saying that SE star SF is equal to minus, right? I don't know why it stopped writing. Just very slow. It's equal to the Kroneker's delta of E and F, and the projection associated to the end of E or F, whatever. Okay. So in order to satisfy this relation, we need this target bijectivity condition. And that's something quite important because it allows us to prove a stronger push-out to pullback theorem that was possible earlier. Okay, now let me get rid of all this writing. And look at one more condition. So I'm now erasing all this. So that it doesn't clutter the screen. Okay. Well, almost. But now, in order to really induce a star homomorphism for a graph C-star algebra, not just Teplik's C-star algebra, then we need one more condition to be satisfied. I apologize for these horrible acronyms. There is a reason to it. So this is for properties, target bijectivity, and this is like a complementary regularity. So of course, it looks like some DNA code, but whatever. It's just what is important that we have a subcategory. I mean, you have to prove it. It's not so obvious that these conditions are satisfied under composition. But that requires a proof that it's a subcategory. Okay, but it's done, can be proven. So this third condition basically tells you that you must not turn an irregular vertex into a regular. Okay, so if something is a sinc or an infinite emitter, then after applying F, it must remain a sinc or an infinite emitter. It cannot all of a sudden be turned to a nice, easygoing vertex that emits finitely many and not more than zero edges. Okay. And this, as you can guess, is now necessary for the satisfaction for having the second Kunst-Krüger relation satisfied. Okay, so now when you have all of that satisfied, yes, we can claim that any morphism between graphs that satisfies all these conditions that belongs to the subcategory, it does induce a star homomorphism on the going the other way around. Between the associated graph C-star algebras. Okay. And now let me give you a very, very simple example of the this construction. So you see, basically, typical example is to have an injective morphism. So considering subgraphs, okay? If you look here, basically, this is a subgraph in there, and this is in subgraph in here. So these graph morphisms that are denoted here with these 4 arrows, all of them are injective, okay? And they satisfy a bunch of conditions. And these conditions are actually known. We call them admissibility, but there is a lot of literature concerning these conditions when your morphism is injective. However, because now we have this target bijectivity condition, it's something which replaces the injectivity assumption. We can do better. And let me give you an example. This is a very recent theorem of Mariusz Tobolski and myself. Mariusz gave a talk about it just a few weeks ago. The upshot of our theorem that we no longer look at, because that's just the union of graphs. And this is a very famous example because this is the Teplitz algebra, which is a quantum disk. This is the Teplitz algebra, which is a quantum disk. So take 2 quantum disks, you glue them over the boundary circle, and you get the Equatorial Podleś sphere, right? That's like the most standard example you can possibly think about. But that's just the union of graphs. Basically, like the union of these 2 graphs, they have this at the intersection, and that's the end result. So it's a push-out, all right? And these are very important statements that you can associate appropriate pullbacks to the unions of graphs, but we can do better than that. So, for instance, what is an allowed morphism is the following. This is, for instance, here, right? Or maybe I should have it more permanent. Imagine that here I have 2 edges, okay? And now I map it over there. So I glue these 2 additional edges to this 1 edge. That's allowed. That's allowed. And in fact, if you think about what kind of map is this, remember that here the functor is contravariant, okay? So this is mapping the Teplitz algebra into the Podleś quantum sphere algebra, which of course exists, okay? This is including a hemisphere in a sphere. So that's perfectly well defined. So such things were not possible earlier, but now we can construct push-outs where these maps are not necessarily injective. Okay, I admit, yes, in order to prove our push-out to pullback theorem, we must admit that at least one of them is injective. So in order for this to work, I would have to add something here, right? Maybe I could add more. Right, this probably wouldn't hurt, but one of them has to be injected in order for the push-out to pullback theorem to work. But that's quite all right, simply because you should remember that in order to apply the Meyer-Vittorius principle, you must have your push-out at least 1 injective or your pullback 1 subjective. If you want to have, say, 6-term exact sequence in K-theory out of a pullback of sister algebras, this pullback must be at least 1 subjective. Okay, otherwise it doesn't work. Okay, so let me now erase it. Or maybe it's not necessary, because here it doesn't go to the other side. Now, how about the covariant conditions? Now, our ambient category is the category of path algebra, of path graph homomorphisms. Okay, so our map goes from finite paths to finite paths. And one of the first things we have to ensure is that we are injective when restricted to vertices. And this is very, very easy to understand because you see the contravariant construction, it basically works like a pullback because you can think of elements in your algebras as maps from finite paths into numbers, okay? So if you have a map from finite paths to finite paths, then you can have a pullback on the space of maps. Okay, so this is how we have the first construction, the contravariant construction. But the covariant construction means that if I have a vertex, oops, this, if I have a vertex V and I map it to W, I guess it's just zoom being slow because I don't know why it doesn't want to write. Anyway, so let me just say it in words. Then you must, if you map V to W, then the projection associated to V must be mapped to the projection associated to W. Okay. And because these projections are assumed to be mutual orthogonal, this map must be injective, because otherwise you'd have a contradiction. Okay. If you would glue two projections, then you would have that these two projections in one graph, they multiply to 0. You map them into another graph, and all of a sudden, because one of the same projection, it cannot multiply to 0. So that's why already from the very start we must be injective on vertices. But these are just vertices that we must be injective on. These maps can be very far from being injective. Okay, there is, and as before. We are cooking up these conditions to make sure that we can pass. So this is just to have a nice covariant factor of the level of path algebras. This is to have a covariant factor on the level of con path algebras, or if you want statics sister algebras. And this takes care of the first type Kunstfigure relation. And here condition is as follows. So we are already in this ambient categories IPG. And now we choose the following condition, that if we take this path homomorphism of graphs, and if we have a situation, this notation means that the path FE prime extends the path FE. Okay, so here goes FE, okay, and FE prime is FE and a little bit further. But it's important that you extend it forward, not backward. This is very important. Okay. And then if you have that FE prime is a path extending the path FE, then these two edges must coincide. Okay. And this allows us to ensure that the first type Kunstfigure relations are satisfied. So now we have a covariant factor from con path algebras to con path algebras. And now here's a big condition. I call the regularity condition. It's as you can see, if you try to read it, this looks very complicated, right? But this is like some legal stuff, right? This is the fine print. If you go to a lawyer to formulate this condition, this would be the outcome. Okay, but I would like to explain to you the gist of what's happening. So let me go back, and I hope that now I can write. You see, traditionally, this condition is as follows. This is only for regular vertices. So imagine we have a regular vertex, we say 3 outgoing edges. Okay. So typically, if you would just restrict yourself to, maybe I shouldn't say typically, this is what's in textbooks, okay? In textbooks, you have these covariant conditions, but assuming that you map edges to edges and you preserve the length of a path, okay? So you are really in the category of graph homomorphisms, not path homomorphisms of graphs, which is a big generalization. What you can find in textbooks that they say, aha, so if I map my regular vertex V to my to another regular vertex FV, then this vertex FV also must emit 3 edges. And then, of course, as you can guess, these 3 edges must be mapped into these 3 edges. Okay, but now we say no. This is too special. We don't like it, and basically, the rule is as follows, that instead of having just edges coming out of a V, we allow paths. Of course, finite paths. So let me just give you an example. So now here on the left-hand side, you start with just 3 edges emitted from the regular vertex V. But when you look at this vertex F of V, also a regular vertex, then, well, it does not emit 3 edges anymore, but it emits 3 finite paths. Okay? We have one, you still have 3 finite paths, and you still have a bijection between the edges here and finite paths emitted from F of V. What is a very important rule and this is why it was so difficult to spell it out. But when you grow your tree of finite paths, okay, you have to remember the following very important rule, which makes it work. Namely, each time you engage a vertex, you must take into account all edges emitted. So there cannot be any other edge coming out of here. It's not allowed, okay? And now, say if you have fewer edges than you have over there, then okay, at one moment you must continue with edges. But again, if you at a given vertex, which is at the end of your first stage edges, if you want to continue your finite path, then you must again engage all edges emitted from this vertex. Okay, so you either continue or you drop. Okay, but you always must. If any vertex in this construction is not the final vertex, okay, then you must take into the picture absolutely all edges emitted from this vertex. And it's kind of obvious if you remember the second type conjugate relation. This is exactly what is necessary in order to have some equalities holding. Okay. So that's just the gist of what happens. And now when you have these three conditions, yes, we have a very beautiful covariant functor from graph system algebra to graph system algebra. He is all spelled out, okay? Okay, and here's an example of what happens. And this example is quite complicated. You see, before, I mean, conceptually complicated. Before it was easy. We really had a push-out diagram. The only thing that we said, all right, it doesn't have to be the union of graphs. We allow some non-injectivity on one leg, okay, on one side, okay? But you really had a push-out diagram, and our theorem is a push-out to pullback theorem, okay? So if this is a push-out diagram and some conditions are satisfied, then if you apply now sister algebras here, sister algebra here, sister algebra here, then you have a pullback diagram, okay? You do it, of course, at all steps, right? But now with these covariant construction, well, you can ask why on earth did we need it? Because I no longer have a push-out to pullback theorem. I simply have a pullback theorem, okay? But we do have a pullback theorem. So here something very funny happens because one pair of morphisms is just the usual. I mean, it's from this previous category, the category used for contravariant construction. And indeed, here I take the sister algebra of this graph. I take the sister algebra of this graph. And the star homomorphism to obtain is given by the contravariant construction. Okay. And this is a nice subgraph in this graph. So it satisfies all these conditions in order for this star homomorphism to exist. Okay. Likewise here, the same happens here. All right. But how about these two arrows? Okay. Well, if I want to have a pullback diagram, then now I should apply a covariant construction. And that's exactly what we do. So we take the sister algebra over here. But now we apply the covariant construction. The construction, we look at morphism from this first graph over here to the second graph over there. We look at it in this category of path homomorphism satisfying all these conditions. And well, I told you that it should be a map from finite path to finite path. Well, here it's the only paths are either vertices or paths of length 1, but I can tell you how this morphism looks like here. Namely, you take your first edge. So here I have countably infinitely many edges going from your left vertex to your right vertex. And say to the first edge, you assign this edge over here. Okay? Then to your second edge, you assign this finite path. Go around the loop and then proceed to the right. And so on and so forth. You can wind around the loop as many times as you want. So you have countable infinity here, have countable infinity there. And this is, you can now verify that indeed this construction satisfies all these conditions over here. So you covariantly now induce a star homomorphism from the sister algebra of this graph to the sister algebra of that graph. And lo and behold, at the end of the day, we do have a pullback theorem. Okay. And this is geometrically quite important because, in fact, this is the CW complex structure of quantum CP2. That's the quantum CP1, or if you want, the standard Podleś quantum sphere here on the left. Okay. This is quantum SU2 or a quantum 3 sphere. All right. And of course, you view Podleś sphere sister algebra, the sister subalgebra in the SU2 sister algebra. What you have here you have a 4-dimensional Hong-Szymański ball, of which this 3 sphere is the boundary. Okay. And so on and so forth. So that's basically what we are doing. We take CP1 and we attach a higher dimensional cell over its boundary to get CP2. That's exactly the CW complex construction. Okay. But you see, what is very important here is that you are really very far from considering subgraphs. Okay. You consider subgraphs only here and there. So these are subgraphs, and here we have contravariant construction. But this is everything but a subgraph. I mean, look, it has infinitely many edges, it has finitely many edges, so that's by no means a subgraph. Okay. So somehow this recipe of going into path homomorphisms, of going beyond the usual graph homomorphism, was always forced on us by these examples. Okay. And this is one of the conceptual challenges, because I somehow would like to invert this morphism. I would like it to go in this direction and have push out to pullback theory. And we can have some attempts on doing it, but it's somehow you have too many paths in there which you don't know what to do. Okay, so that is one of the things to be sorted out. Okay, so now we come to the main research objectives as stated in the project. And again, here maybe I should mention that we do have some flexibility, right? So whatever we planned, if during our research it turns out that we can prove something else, maybe even more interesting, then we just do it. We are not bound to prove exactly what we wrote here. That's just a roadmap. Okay, it's kind of like archaeology. You must have a plan of where you want to dig in order to get sponsors to give you money. But the moment you start digging and you see that there's nothing there, but you have Tutankhamun next door. I mean, the pyramid is just 100 meters to the left, and you dig to the left, even though it's not written in your project. Yeah, so this is very important. But let's see what have we promised thus far. But we develop new and most general concepts of morphisms of graphs that make the assignment of graph sister algebras to graphs either contravariant functor, turning pushouts of graphs into pullbacks of graph sister algebras, or a covariant functor respecting limits. So that's some work already in this direction is done. And our second research objective in this work package is to unify push-out to pullback theorems by proving them for higher rank graphs, allowing both sinks and infinite diameters. So here I have to comment, you see, when you look at this push-out to pullback theorem, there is a work by Aidan Sims and his collaborators doing it for higher rank graphs, but he has some strange assumptions which we don't need in the usual graphs, like no sinks. Okay, for us it's very bad to have no sinks because you really rule out some very important quantum topological examples. So non-commutative topology needs sinks. I mean, quantum disks, quantum balls, they all have sinks. Okay, so you don't want to get rid of sinks, and we don't need to get rid of sinks to prove our push-out to pullback theorem. So that would be nice to generalize our methods to higher rank graphs and combine it with what Aidan and his collaborators did. So let me end by discussing some first steps which came to my mind, first research steps that we can do, first things that are not really known yet. So as the most obvious part, I would mention, and this is what I hope to do with Mariusz very soon, is to have more examples, interesting examples of non-injective pushouts with breaking vertices. Because if you go back to our push-out to pullback theorem, yeah, which is over here. Well, we want to go well beyond such cases like we have for gluing quantum disks into quantum spheres. So first, we want to allow this non-injectivity on one side. That's in the spirit I just showed you. But secondly, there is the whole yoga of how to handle infinite emitters, okay? Because infinite emitters can be your breaking vertices. And basically, there's a rule of thumb. So this was also discovered by Jack Spielberg and his PhD student, that if you have breaking vertices, so you see, you look at one graph inside, say, the left graph, and you might have some breaking vertices over there, but then you look at the same graph inside the other graph, and then again, you look at breaking vertices for this inclusion or for this map. And what is very important that if something is a breaking vertex for the left, it must not be breaking vertex for the right, and vice versa. Okay, so that's how you can handle breaking vertices, and you can have breaking vertices, and everything works. Okay, the proofs are becoming far more complicated because when you have breaking vertices, then these induced star homomorphisms are far. I mean, the ideals by which we have to divide are more complicated, so you have harder work to prove that you really have a pullback, because you have to check Peterson's conditions, which are about these sister ideals. Okay. So first, I would just, I hope Mariusz agrees with me that what we really need to do very urgently is to have just a bunch of interesting examples which would fully utilize the generality of our theorem. Okay. So that's first research step I suggest. Okay, the next one is something which came out of the talk of Jack Spielberg. If you remember, he gave a talk some weeks ago, I think in 7th of December or something like this. And they have a construction for turning push-outs into pullbacks, but for relative graphs, okay? So basically what you do, you take your graph. In your graph, you take your set of vertices. In your set of vertices, you take the set of regular vertices. And then you take a subset in your set of regular vertices. And only at this subset, or maybe beyond this subset, whatever, just a matter of convention, you implement the Kunz-Krüger relations of a second kind. So you are sort of in between Kohn-Path algebra and Leavitt-Path algebra. You're in between Teplitz-Path algebra, Teplitz graph sister algebra and graph sister algebra, okay? However, there is a general theorem that every relative Kohn-Path algebra is Leavitt-Path algebra for a modified induced graph. So every Teplitz sister algebra for a relative graph is always graph sister algebra for a modified graph. The general construction is quite complicated, though straightforward and explicit, but let me just give you a very simple example. If you take this graph, so just one vertex and one edge, of course must be a loop, okay? And then you implement only your first Kunz-Krüger relation, then it's the Teplitz algebra, because you just have one isometry condition, okay? But if you would take both Kunz-Krüger relations, then this isometry would be unitary, and this is the sister algebra circle. That's not the Teplitz algebra. But by this construction, you know, of extending graphs, you construct this graph. So applying this induced graph construction, you get this graph, okay? And now if you take the graph sister algebra of this graph, that's the Teplitz algebra. So it's the same as that sister algebra, okay? And you can do it for any graph. So whatever relative Kohn-Path algebra you take here for any relative graph, you can always construct the new graph such that this will be isomorphic to the Leavitt-Path algebra of this more fancy graph. Okay. So when Jack and his student proved a push-out to pullback theorem for relative graphs, we suggested the following: that one should translate his conditions from these relative graphs into the induced graphs. Okay. And see if they give you conditions which are more relaxed than the conditions we have for push-out to pullback theorem for the usual graphs. Because you see, you should view, if you look at all possible graphs, inside all possible graphs, you have some subset of graphs which are images of this induction. Okay, so not every graph will be an induced graph from another graph. Okay, so somehow this way you restrict your class of graphs, and maybe this means that you can relax your conditions for having a push out which induces a pullback. Okay, so that's a research proposal that we agreed on during Jack's talk. Okay, so let me raise it now. Okay, that's something that Alex Frey is working on. So Soren, you should be aware of it, right? That there is an older paper of Robertson and Szymański about kind of push out to pullback theorem, but for Kunz-Pimsner algebras. Okay, so instead of graphs, you have something more general, and gluing of these pieces will give you pullbacks of Kunz-Pimsner algebras. And Alex has somehow an idea of how to generalize of what we did in our push out to pullback theorem to Kunz-Pimsner algebras, at least under the injectivity assumption. So maybe a good research project with Alex would be now to do it without the injectivity assumption. Okay, next. You see, I did my best to have these conditions as general as possible. Okay. But even though I took utmost care to introduce only as many assumptions, and I really need to prove that I have an induced map star homomorphism of graph sister algebras, you see that some things are missed. Okay, and let me draw you an example. I told you that when we look at path homomorphisms of graphs, we need not map edges into edges. We map edges into paths, okay? Well, typically, I mean, not typically, you might map them into longer paths, but nobody can stop you from mapping an edge into a vertex, okay? And in particular, if you look at, say, a graph where you have just one loop, okay? And a graph where you have just one point, all right? Then this is perfectly okay. To map this graph sister algebra, which is continuous functions on the circle, into this graph sister algebra, which is just complex numbers. I mean, you have evaluation map. It's a commutative sister algebra. Evaluation maps exist of commutative sister algebras. Okay. And if you look at it carefully, that's just evaluation at one. Okay. Which would give you such a map. There's covariant here, okay? So basically, I believe what we can do is that we can attach single loops to any sinks and then collapse them, okay? So I can have, I don't know, I can have something more fancy. And have two things over here, and then I say, all right, so now I attach loops here and there, okay? And what I do, I collapse them. So and as far as I can see, this allows you the preservation of all Coulson-Krüger relations. It doesn't fail them, okay? And it was not allowed, it's actually not allowed in my conditions for the covariant functor construction. So we can make at least one more step to make these conditions more general. Okay. And now, since I have 1 minute left, let me state the first step I would like to mention right now. Namely, you can take this Kirvasitu-Hajac-Tobolsky pullback theorem I told you about on this example of a CW complex construction for the quantum CP2. And you can try to do it for higher rank graphs, starting with trimmable graphs. And let me tell you what I have in mind. So at least Francesco and Mario should immediately know what I'm talking about. Just let me go back to this graph. For this one. You see, these sister algebras are fixed point sister subalgebras in some graphs, other graphs. So basically, here what we can do, we can take five-dimensional sphere, and here we can take three-dimensional sphere, and here we take the tensor product with S1, here take the tensor product with S1. And now what we have another pullback diagram. We have a theorem which is good for trimmable graphs. So the only thing that somehow is not fitting is that I do have tensor products. And as I'm sure all of you know, the category of graph sister algebras is not close with respect to tensor products. This is exactly why you have higher rank graphs, okay? Because you have this beautiful construction that if you take graph sister algebra of a K graph and tensored with a graph sister algebra of an L graph, then there exists a natural construction of K plus L graphs such that this tensor product will be nothing else but the higher rank graph sister algebra of this K plus L graph. Okay, so if I go from projective spaces to spheres, to odd spheres, then I have to add tensor product with circle algebras over there, which puts me out of the category of graph sister algebras. But I'm still in the category of higher rank graph sister algebras. So this would be like the first step in order to generalize this pullback theorem to higher rank graphs. And my time is up. Thank you very much. If you have some immediate questions, ask me, but if not, then Matthias will stop recording. Okay, so please stop recording.